Imagine, for a moment, that you are watching and listening closely. Night has fallen, and above you stretches a canvas of endless stars. The Milky Way spills across the sky in a pale river of light. As you gaze upward, you realize with a shiver of awe that everything visible, every twinkling star, every glowing nebula, every galaxy, is only a tiny fraction of what's really out there. Most of the cosmos is hidden in darkness. Not the darkness of empty space, but something deeper and far more mysterious. An invisible mass and a phantom energy that seem to shape the universe. What are these unseen forces that bind the galaxies and drive the expansion of the cosmos? The quest to find out is one of the greatest scientific adventures of our time, and its answer could upend our understanding of reality. It's a story about everything we don't know, and why that's so thrilling. So if you're ready, let's venture together into the dark and see what we find. And if you'd like to help me bring more of these mysteries to life, don't forget to like, comment, and subscribe. Our journey begins nearly a century ago, when astronomers first sensed something uncanny lurking in the darkness. In the early 1930s, a Swiss astronomer named Fritz Zwicky was studying a distant cluster of galaxies known as the Coma Cluster. He measured how fast those galaxies were moving, and got a shock. They were racing around so quickly that, by the laws of physics, the cluster should have flown apart. There simply wasn't enough visible matter, stars or gas, to hold those galaxies together with gravity. It was as if an invisible glue was keeping the cluster intact. Zwicky proposed a bold idea. Perhaps some unseen dunkle Materie, German for dark matter, provided the missing gravity. It was a radical suggestion, and many scientists at the time found it too strange to believe. After all, how do you prove something exists if you can't see it? For decades, Zwicky's idea remained on the fringes of astronomy, a curious hint of an invisible universe, but not yet solid evidence. Fast forward to the 1970s. American astronomer Vera Rubin began measuring how stars move in spiral galaxies, and she noticed something odd and world-changing. Stars at a galaxy's outskirts were orbiting just as fast as stars near the center. By all rights, those outer stars should have been flung off into space, unless there was far more gravity than met the eye. Rubin had rediscovered Zwicky's invisible glue, but this time within individual galaxies. The evidence was stark. Each galaxy seemed to be embedded in a huge halo of unseen mass holding it together. One by one, other astronomers confirmed this pattern. The presence of dark matter, whatever it was, became the only explanation that made sense. Zwicky's once ridiculed idea had been vindicated, and the scientific community had to accept an astonishing truth. The vast majority of matter in the universe is invisible and unknown. As the evidence grew, dark matter went from wild theory to pillar of our cosmological model. Astronomers found that entire clusters of galaxies contained far more mass than we could see, and even light itself could be bent by the gravity of unseen mass, a phenomenon called gravitational lensing. In 2006, a striking observation known as the bullet cluster collision provided a dramatic snapshot of dark matter's reality. Two clusters of galaxies had slammed together at high speed. The hot gas from the clusters, which is normal matter, crashed and slowed down, but the bulk of the mass sailed through unaffected. When scientists mapped the mass distribution, they saw that most of the mass was separate from the visible gas, as if ghostly matter had passed straight through without colliding. It was one of the clearest signs that this dark matter is something real, something that doesn't interact with light or normal matter except through gravity. By now, scientists could map where the dark matter is. We even believe it forms a cosmic web of filaments across the universe, a hidden scaffold on which galaxies are assembled. Yet the burning question remained: what exactly is dark matter? We knew it was there, but we still had no idea what it's made of.
While astronomers were grappling with that enigma, another even more shocking mystery was unfolding. In the late 1990s, two independent teams of researchers were studying distant exploding stars called Type Ia supernovae to measure how fast the universe has been expanding over time. They expected to find that expansion was slowing down, ever so gradually due to gravity. Instead, they found the opposite. The expansion of the universe is speeding up. Distant galaxies weren't just receding, they were accelerating away from us. This was so bizarre that at first the scientists themselves didn't believe it. But observation after observation confirmed it. Something was propelling the universe outward, overcoming gravity on the largest scales. This something was dubbed dark energy, because we had no idea what else to call a force, or energy, that acts in the darkness of space to push everything apart. The discovery of dark energy hit the scientific world like a thunderbolt. Suddenly, it seemed that about 70% of the universe was this unknown dark energy, dwarfing even dark matter, around 25 to 27%, and leaving only a few percent for all the normal matter we actually see. It was a humbling and almost absurd revelation. We humans, with our telescopes and equations, had only been accounting for a small sliver of reality. To explain the accelerating cosmos, physicists resurrected Einstein's cosmological constant, a sort of built-in energy of space itself that Einstein originally introduced and later retracted to make the universe static. Now it appears such an energy really did exist in nature, driving galaxies apart. Yet calling it a cosmological constant or vacuum energy was just putting a name on the mystery. What was this dark energy really? Was it truly constant, or something that changes with time? Why does it have the weirdly tiny value that it does, instead of 0 or a tremendously larger number? These questions plunge science into a deep contemplation that continues to this day. By the early 21st century, our view of the universe had transformed. We now had a cosmic inventory that was frankly startling. Roughly 5% normal matter, everything from stars to planets to interstellar gas, about 27% dark matter, and about 68% dark energy. In other words, all the glowing galaxies and familiar stuff are just a thin frosting on a vast cosmic cake, dominated by dark ingredients. It's as if we had been studying the tip of an iceberg, without realizing the enormity beneath the surface. This realization launched new efforts across physics and astronomy to investigate the dark universe. Scientists devised ingenious experiments deep underground to hunt for dark matter particles, and ambitious sky surveys to measure the effects of dark energy on the history of cosmic expansion. So, what have we learned so far about these shadowy components? Let's start with dark matter. We know what it does. It pulls things together with gravity and form structure. But what is it fundamentally? The leading idea is that dark matter is some kind of particle, a new type of elementary particle that isn't part of the usual roster of protons, neutrons, electrons, or even neutrinos. If so, it must be very special. It doesn't emit light, doesn't absorb light, and barely interacts with any normal matter at all. Trillions of dark matter particles could be passing through you every second, and you'd never notice. capturing one is exceedingly hard, like trying to catch a shadow. Physicists have built huge detectors, often placed deep underground to shield them from interference, hoping that once in a great while, a dark matter particle might collide with an atom inside and leave a tiny telltale signal. So far, these detectors have seen only silence. Every time we think we've cornered dark matter, it slips away, forcing us to build even more sensitive experiments. This elusive behavior is actually part of the intrigue. It suggests dark matter might belong to a realm of physics we haven't yet unlocked. Dark energy, in its own way, is even trickier to investigate. We can't bottle up a piece of dark energy in a lab. Instead, we observe its handiwork across billions of light years. Scientists have become cosmic surveyors, measuring the brightness and distances of far-off supernovae, mapping how galaxies cluster, and scrutinizing the afterglow of the Big Bang, the cosmic microwave background, for subtle clues. All these lines of evidence so far point to the simplest explanation. Dark energy acts like a constant, an unchanging energy embedded in space itself. If you double the volume of a region of space, you get double the dark energy, as if it's just part of the fabric. But is it truly constant forever? That's a question we're trying to answer. New telescopes like the Vera C. Rubin Observatory on Earth and the European Euclid Space Telescope, launched in 2023, are set to map the universe's expansion and the distribution of matter more precisely than ever. They'll watch how dark energy might have subtly changed from billions of years ago to today. If we detect that dark energy was different in the past, that would mean this energy is evolving. Perhaps a clue that it's a dynamic field or force rather than a static property. Early hints from recent data have even suggested a possibility that dark energy might be strengthening or weakening slightly over cosmic time, though nothing is confirmed yet. We're truly in the realm of the unknown, designing experiments as our compass to navigate this darkness. Naturally, scientists haven't been content just to observe. They're also theorizing like crazy. Both dark matter and dark energy have sparked a myriad of theories, each trying to illuminate what these things could be. For dark matter, one popular hypothesis for years was a class of particles whimsically named WIMPs, weakly interacting massive particles. These would be heavy, slow-moving particles that interact only through gravity and the weak nuclear force, making them essentially invisible. WIMPs were appealing because some theories of particle physics predicted them, and they would have the right properties to produce the amount of dark matter we observe. However, extensive searches in underground detectors and in powerful accelerators like the Large Hadron Collider have yet to find any sign of WIMPs, putting that idea in jeopardy. Another idea involves ultralight particles called axions, which were originally proposed for other reasons, but could also form a gentle, pervasive, cold cloud of dark matter. Experiments are ongoing to detect faint signals of axions, converting into light under magnetic fields. Then, there are more exotic proposals. Perhaps dark matter is made of many different particles, or something like hidden, dark atoms that don't interact with regular atoms. A minority of scientists even suggest that what we call dark matter might not be matter at all. Instead, maybe our theory of gravity needs tweaking. They point to theories like MOND, modified Newtonian dynamics, where under low acceleration, gravity works slightly differently, possibly explaining galaxy rotations without invoking invisible mass. But such theories have a hard time explaining cosmological observations like the cosmic web or the bullet cluster's evidence. At the end of the day, most researchers think dark matter is something real and particle-like. We just haven't caught it yet. In the face of such enormity, one might ask, will we ever truly know what dark matter and dark energy are? History gives us reason to be optimistic. We've solved great mysteries before. We discovered what atoms are made of. We unveiled the nature of stars. We found particles like neutrinos that were once just theoretical. Each time it required new technology, new thinking, and often decades of effort. But we prevailed. Today, thousands of brilliant minds are on the case, using every tool at our disposal, from subterranean detectors to orbiting space telescopes, to chip away at these problems. Perhaps tomorrow or years from now, a breakthrough will happen. A dark matter particle finally rattles an atom in a detector, or a telescope catches a subtle twist in the light of distant galaxies that reveals dark energy's true face. The moment we finally understand these dark forces will be one for the history books. It could trigger a paradigm shift in physics as profound as when we learned the Earth orbits the sun, or that quantum mechanics rules the tiny world. It might even open the door to technologies or insights we can't yet imagine. Until that day, we live in a universe that keeps its secrets close. But maybe that's for the best. It leaves us with a sense of wonder. The night sky would not be nearly as captivating if we knew all its stories. Imagine standing under those stars again, knowing that in the darkness between them lie answers to questions we haven't yet asked. The mystery of dark matter and dark energy invites us to keep exploring, keep questioning, and keep our sense of awe alive. So what do you think? Will we one day uncover the true nature of dark matter and dark energy? Or will these cosmic secrets continue to elude us? Let's talk about it in the comments.